Hello, 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 hello. So here is the follow-up problem on the previous problem. The previous problem, we had a ring, circular ring, charged with a charge Q. And the question was, what is the electric field at the center of that ring? And also, what is the electric field at a vertical distance above that plane through the center? And I gave you dimensions. And the dimensions that I gave are similar to the dimensions that I will give you today. Ready? This is a perfect square. This is 1 meter, 1 meter, 1 meter, 1 meter. So this here, AC, is 0.5 meters. I put on this square a total charge of plus 2 microcoulomb, 2 times 10 to the minus 6. If these were conductors, the charge would not be uniform throughout. It may not differ a lot, but it would not be exactly uniform. For instance, here at these sharp turns, the charge density would be higher. So to avoid that issue, I'm going to propose that this square is a non-conductor, and that I, Walter Lewin, distribute on the 4 sides 2 microcoulomb, and that I do that in such a way that the charge density is everywhere the same. So I make the charge distribution uniform. So the amount of charge that is on 1 centimeter here, or there, or there, or there, or there, or here, will all be the same. The question is very similar to the previous problem. What is the electric field at the center C? And what is the electric field at this point P? I want to know magnitude and direction. And the separation C to P is 0.8 meters. So if you look at my previous problem, you will see these 3 dimensions for the circle. So I would predict, and I'll be very honest with you, I haven't worked this yet out numerically, but I would predict that the electric field at that point P will be different from problem 1, where we had a circular ring. In that case, we found that the electric field at point P was vertically pointing up, and it was 1.71 times 10 to the 4 volts per meter. Therefore, I now predict, but honestly I haven't worked it out yet, that surely, in this case, it will be different. But it will not be wildly different. So if you find an answer for P, the electric field at P, which is wildly different from 1.71 times 10 to the 4th volts per meter, you have probably made a mistake. Okay? So I'm going to work it out myself, and then I will record the solutions later today. When I will post this problem, I do not know. Probably sometime in December, maybe even January 2019. I really don't know yet. I just woke up, I'm still in pajamas, I put my morning hat on, and surely we will be friends. But that goes without saying. I forgot to mention that I'd like 3-digit precision for the final answer, just as we did on the last problem. If you compare the result of the E field at point P with the ring, with radius ½ meter, with the E field at point P with the square, which have sides 1 by 1 by 1 meter, then it should be obvious that the E field at point P in the case of the square should be lower than in the case of the ring. In the case of the ring, it was 1.71 times 10 to the 4 volts per meter. It should be lower, and the reason is that in the case of the ring, all points on the ring had a distance to the center of the ring of exactly ½ meter. In the case of the square, there are only 4 points that are exactly ½ meter away from the center. All others are farther away. And so that translates immediately that the average distance to point P from the charge is larger than the average distance in the case of the ring. And since the average distance is larger in case of the square, that translates, of course, into a lower electric field. And when I did my solutions, which I just finished, that was the first thing I checked. Indeed, it's lower. And again, if the two values, the ring and the square, differ by a huge amount, you gotta make a mistake. You made a mistake. All right, but it is lower in case of the square. All right, take care.